Hi! In this video, we are going to start the discussion on the origin of the universe. But in this video, we will focus first on what happened before the solar system. Because remember, the last video was about the origin of the solar system. And again, ultimately, we say that the solar system, or any solar system, not just our solar system, started from a nebula, right? Or a cloud of dust and gas particles that are floating around in space. But again, that begs the question, where did that nebula or where did the gas particles come from, right? So we will address that first, okay? So to answer this question, we have to go back at what we know about stars, right? The star cycle, which I know you happen to study in grade 9, right? In one of the quarters in grade 9. So this is the star cycle, or this is the life of a star. So if you have a star, so let's just take a sun-like star because, it's more familiar. That started from a nebula, right? And then it formed into a star, right? And then sometime that star might become a red giant, and then that red giant might explode, or not might undergo a process which would create planetary nebula, and what is left of it is a white dwarf, right? So basically the outer layers will explode, or will move outwards in an explosion. For the lack of words to explain, you'll just use the word explosion. The outer layers will explode and be scattered all the way around, but the center remains a star. It becomes a white dwarf, right? But you could also have another thing where you have a star forming nebula, and it will form a massive star, a very big star, and that big star will become a red supergiant, and then it will explode into a supernova, which, depending on its size, could leave behind a black hole. So it's kind of like this, where you make a planetary nebula, but what is left is a white dwarf. Here you create a supernova, but instead of a white dwarf, you create either a black hole if it's very, very massive, if or it could create a neutron star, or it could just create a nebula, right? Meaning nothing is left, everything is obliterated. But that's the idea. So what we are trying to input, what you're trying to look at here is, what we're trying to imply is that, where do nebulae come from? They come from other stars when they are also dying. So this is a cycle. So a nebula forms stars, the stars mature, they die, they explode, and contributing gas particles and dust particles to space, which would eventually form a nebula, and then that nebula again forms a star. So there's this cycle of stars, and in fact, our own solar system, according to scientific estimates, our star would have to be a second or third generation star. What it means by that is, in the life cycle, the sun would have been a second generation or a third generation, meaning the earliest stars matured, died, creating the second generation of stars. Then the second generations matured, exploded into using a supernova process, and created the third generation. So we estimate that the Earth the sun is either a second generation or a third generation star. Okay, so that answers the question, where did the nebula from which the solar system was created from, where did the nebula come from? It's from this cycle. So you have nebula forming stars, stars maturing, and then stars die, and then creates nebula, because after all, when the upper layers of that star explodes, right, or is cast out because of a shock wave, those particles would be scattered all around space, and that they would create dust particles. Okay, so you have to remember that in grade 9 you also kind of discussed about the layers of the Earth. So what happens is, hydrogen gets fused and becomes helium. Heliums get fused, become other layers until it becomes carbon, and then oxygen, and then silicon, and then finally it becomes iron. So iron is the kind of the last in the chain of that element formation, right? So let's try to understand why this is. I know you have some discussions in grade 9, but let's try to discuss why this is, because this is important later on. Okay? So, we have to kind of understand first what happens. What is hydrogen? Well, hydrogen is it's an atom, right? It's an element, helium, carbon, oxygen. And essentially, atoms or elements are made up of neutrons, which are represented by the pink circles here, and protons, which are the blue ones. Okay? Now, scientists actually discovered that, for example, if you take this, and I would imagine this is lithium because it has 3 protons. Remember, 3 protons means element number 3, which in the periodic table is lithium. Remember, hydrogen, helium, and then lithium. So this is lithium. This is a lithium atom, and this is specifically lithium 7 atom, right? Because you can see it in the diagram. It is lithium with 3 protons, and it happens to have 4 neutrons. That's why the mass is 7, right? Well, look at that. You have 4 neutrons, the pink ones, and 3 protons. So you would write it like this: 3 protons, 4 neutrons, 7 nucleons all in all, right? Now, what is weird about this is we can weigh in the laboratory what is the weight of a lithium 7 atom. Okay, so let's say the weight is X. Okay, let's not bother with the numbers, it will just make us confused. And then take note that this lithium 7 is made up of 3 protons. And let's make the proton dark. And 4 neutrons. 2, 3, 4. And guess what? If you get the mass of the proton, okay, multiply it by 3, because after all, there are 3 protons. Get the mass of the neutron, multiply it by 4, because after all, there are 4 neutrons. You know, get the sum, let's say A and B, and then add them, C. Obviously, by logic, you should realize that this is the same. Because after all, a lithium 7 atom is just made up of 3 protons and 4 neutrons. So if you weigh 1 proton and you get that weight multiplied by 3, that represents 3 protons. If you get the weight of 1 single neutron and multiply it by 4, so you get the weight of 4 neutrons. And therefore, if you get the weight of all the 3 protons and the weight of all the 4 protons and add them, you should get the weight of the whole lithium 7 atom. Okay? Right? It's logical. The problem is, when scientists look at this, guess what? When you look at the mass of the nucleons that are separated, not in an atom configuration, the mass is greater. Right? So it's heavier than when they are binded together as one atom. Okay? So let me get that straight. There is, in terms of the components, this atom is made up of 3 protons and 3 neutrons. If you weigh the 3 protons and 3 neutrons separately, they're not binded in an atom, it still is made up of 3 protons and 4 neutrons. So again, it's weird that when we look at this in the lab, this actually has a smaller mass than this, which is weird because, again, let me reiterate for those of you who haven't realized it yet, lithium 7 is just made up of 3 protons and 4 neutrons. But if you weigh the 4 neutrons and 3 protons separately, when they're not binded in an atom, add them, get a mass, and compare that to the mass of a lithium 7, they are not equal. this is heavier, sorry, this is less massive than this. So the sum of the parts is not equal to the whole. Right? And because of this, we say that there is a missing mass. Right? Missing mass, that means that, okay, let's put numbers so that, because it's actually easier this time. But again, these numbers are not accurate. I'm just using this tool as for that, so that it would be easier to understand. So for example, C is, let's just say 12 units, whatever that unit is, what that unit is. X is just 11 units. So you see, the mass of the individual particles that constitutes that atom is higher, it's 12, than this. Probably it's closer to something like, the mass here is 7, here it's 7 point. Again, I'm just making this up. Don't rely that this is correct or anything. But it's 7 point something. So again, the difference is small, but there is a difference, right? And scientists have been trying to eliminate this difference. To at first they thought it was just a statistical thing, so they made sophisticated and sophisticated and more sophisticated instruments to do this. But guess what? The thing still persists. Meaning, if I simplify it, let's say I'll just take one proton, one neutron, right? The mass of this one will be higher. It would be something like 2 point something AMU. But if you get the same, bind them together to make helium 2, that's helium 2, hydrogen. Hydrogen 2, hydrogen with one proton, one neutron, so hydrogen 2. Its mass is just 2 AMU. So there's this difference. And again, this is always heavier than that. Okay? So there's this problem of missing mass. Okay? And then again, I don't want to discuss this in separation with other concepts. I want to remind you that Einstein invented this formula E equals mc squared. Okay? And E is energy, m is mass, c is the speed of light. The speed of light is a very big number. It's 300,000 or 300 million meters per second, 3 times 10 to the 8 meters per second. So this is already a big number. So if it's a big number, and then you square it, so it's like 3 times 10 to the 8 times 3 to the times 3 times 10 to the 8. So you square that. So it becomes an even bigger number. So you multiply that with the mass, you get an amount of energy. Right? So it's a calculation thing. So therefore, here you have a mass difference, right? You have a mass difference. That mass difference, that's small, yes, given that that's small. But even with a small mass, even if this is small, because you're multiplying it with something big, you will still get a big amount of energy. Okay? And scientists were perplexed about this one. And then they realized that maybe what is missing here, because if you think about it, this configuration has more of it. This configuration has less, right? This has more mass. This has less mass. So therefore, scientists, just logically thinking about it, if this has more and this has less, maybe there is something here that we don't see that compensates why it has less. Yeah, logic. If this has more mass and this has less mass, maybe this has something else that we don't see, and that something else compensates for why it has less mass. And in fact, they recognize that that is because this one is a configuration where the two are bonded together. This is a configuration where there's no bond between them. So what's the missing? The nuclear bond. Because think about it, this two are not bonded together. These two are bonded together. So what is present here that is not in here? It's a nuclear bond. So now scientists are realizing that, okay, I see what's happening here. What's happening is the missing mass, because this is more, right? That missing mass, or let's represent it in another way so that it's easier. So maybe the mass of this is 2 AMU plus more, plus X. While this is just 2 AMU because, you know, it has less mass. What's happening here is that missing mass, that X, actually was used to form the nuclear bond. Or that missing mass is what is quote-unquote converted to become the nuclear bond between the two nucleons. Okay? And this energy is big because even if the missing mass is small, again, because of Einstein's equation, even with a small mass, you multiply it with something big, the speed of light, and not just the speed of light, but the square of the speed of light, you will get a big amount of energy. So therefore, it has a lot of energy. The bond inside the nucleus has a lot of energy in it. And in fact, that's why we call it the strong nuclear bond, the strong nuclear force. In higher physics, there are only 4 fundamental forces, which is electromagnetic force, gravity, strong nuclear force, and weak nuclear force. Okay? So the fact that this bond was coming from the missing mass, and Einstein postulates that a small mass, even with a small mass, multiply it with the speed of light twice, you get the amount of energy. That means this bond here contains a lot of energy. It's very strong. That's why again we call it a strong nuclear bond. So that's the idea. So the idea is, when two particles, nucleons, neutron and a proton bind, some of its mass will be missing because some of that mass will be converted to energy, and that energy is contained in the nuclear bond. But again, I know this is a difficult concept because, you know, you are still in high school. And again, my goal here is not really to make you understand this fully, but I just want you to appreciate how beautiful that concept is. Obviously, if you want to know the details, what I'm telling you here is kind of not accurate at all. There are some inaccuracies about this that you would only discover when you study this more in senior high school or in college. But for the purposes of just kind of capturing your interest and convincing you that physics is fun, that you should take a physics degree when you are in college, this is enough. Again, logic. This configuration, not bonded, have more mass. It's heavier than when they are bonded. So therefore, again, logic would tell you, okay, if this is more and this is less mass, maybe this has more in it that we don't see that compensates for why it has less mass. And obviously, we know that what is missing is the bond because these two are not bonded and this is bonded. So therefore, what is missing here is the bond. So therefore, we are saying that the mass here that was missing probably were used, quote unquote. And again, these terms used, converted, is a little bit misleading. It's a little bit not correct to the concept. But for high school physics, it's enough. This missing mass is kind of used, converted via the equation of Einstein, mass multiplied by speed of light. And again, that missing mass is very small, but this is very big, square of the speed of light. So you get a very big amount of energy. And that amount of energy is actually the energy that holds the two nucleons together. And that is what we call the strong nuclear force, the nuclear bond that bonds them. Okay? Okay, so I know that is kind of way off from our concept of the origin of the universe, but you would soon understand why that is important. Okay? Now, The next thing that I will show you is a graph of the binding energy of all the elements in the world. Okay? This is the graph. I'm sorry. That's a graph. Okay? And if you look at this, this is the mass number. So meaning, for example, helium-2. Helium-2 will be somewhere here. Not helium-2, sorry. Hydrogen-2, right? Hydrogen with a mass of 2 will be somewhere here, so 2. Okay? And then if you have, for example, I don't know, boron 10. I'm sorry. Sorry, not boron. Beryllium. Beryllium is number 4. Boron is number 5. Beryllium 4. 4 protons, 6 neutrons, and then 10 nucleons all in all. Then it would fall somewhere here. Right? This is 10. Okay. So if you notice, this is now a graph of the nuclear binding energy per nuclear particle. Okay. So if you notice, the pattern is as you go from mass 1 up to iron, right? And iron is element number 23, if I'm not mistaken. Maybe I am mistaken, so let's just search for it. Element number iron. So iron is actually element number 26. I'm sorry. Element number 26 is iron. So so it has 26 protons, and it depends what isotope the number of neutrons. But the point is that that's the idea, that you have this iron group. And in fact, well, I did not need to search it. It's actually written here. So iron 56, right? Which means 26 protons, and then, you know, you just subtract 56 minus 26, so that's 30. So 26 protons, 30 neutrons, and 56 all in all. That's the top. What that means is that's the element with the highest amount of binding energy. So it's the strongest element. So the binding energy in the nucleus of that element is the strongest among all the elements, all the isotopes. Specifically, iron 56. Okay? So I'm not sure if this is iron 56 or they mean iron 58, but from the looks of it, it's iron 56, right? And again, I don't really memorize this stuff. You might say, why haven't you memorized this? Again, for me, it doesn't make sense. For me, memorization is not really that important. What's important is you understand that there is this curve of binding energy, and in all the elements, the highest binding energy is iron. Okay? And you might say, okay, sir, we have been trying to discuss supernova, we have been trying to discuss the origin of the universe, and then now you're discussing to us what missing mass is, what binding energy is inside the nucleus, and then now the amount of binding energy here. What is its connection to what we have been discussing? Well, look at this. You always notice that in stars, it's always iron at the core. Okay? You always notice that in stars, the core will always be iron. So the end of the process of fusion always ends up with iron. And the reason for that is precisely this graph. If you look at this graph, the top of the binding energy, the highest binding energy, is iron. Okay? The highest binding energy is iron. Okay? And why is that important? That's important if you want to understand what fusion does. Okay? So what fusion does is you have, for example, hydrogen, and hydrogen would fuse together. And hydrogen is element number one. Hydrogen is element number one. So element number one plus element number one, it will become element number two, helium. Okay? That's the reason why in this here, you have hydrogen, and then the layer below it is helium, because you have fused helium. And then carbon, right? Because again, all you need to do is, for example, well, there is other ways of doing this, but I'm just showing you one way. So if you have helium plus helium plus helium, that's element number two, element number two, element number two, you would eventually get to carbon, which is element number 6. Right? So they are fusing. But more importantly, when you fuse something, why would you burn? Or why would you get the effect that the star produces energy? Or, it's burning. Again, it's not really burning because it's not combustion. But when you fuse something like hydrogen and hydrogen, you get energy. You get energy. Right? So when you fuse hydrogen and hydrogen together, you get energy. Right? And this energy is the energy of the star. Okay? Now that has to do with the binding energy. So if you look at this, the binding energy of hydrogen is so low. So the binding energy of helium is a little bit higher. Okay? And the binding energy of the next, like carbon, is a little bit higher. So what do you mean by binding energy, sir? It's the energy that holds the nucleus together. Okay? Think of it as like a ball. There's a spring. Obviously, that spring would try to push this ball A and ball B. Obviously, that spring would try to push A and B away. Right? And remember, for example, if you have helium, helium is made up of 2 protons. And you see positive and positive. And if you have learned something from your grade 8, it's that same charges would repel each other. So this positive would push the other positive away. So they would try to repel. And what you're doing is you're kind of putting a string that holds them together. Okay? Preventing them from falling apart. Okay? So imagine this is a proton and that's a proton. That's proton, that's another proton. So just because they are positively charged, they would try to get away with each other. But what you're doing is you're fastening them with a string. And what is that string? In this analogy, that string is the bond. It's the nuclear bond. It's the nuclear bond that holds the protons together, or the nucleons in general together. Okay? So therefore, think about it. What's the difference when this bond is weak and if this bond is strong? So if this bond is weak, if the nuclear bond is weak, it means this nucleus would disintegrate. It would break because the nuclear bond will not be strong enough to keep their repulsion. Right? But if this is strong, that means the nuclear bond will be able to overcome their repulsion and the atom will stay. I mean, the nucleus will stay. Meaning, what is my point? My point is, if we have a weaker nuclear bond compared to a stronger nuclear bond, A weaker nuclear bond represents an atom that is less stable. Right? Because think about it. If the bond is weaker, then the particles that are being bonded together can have an easier time of overcoming that bond. But if you have a stronger nuclear bond, that means the atom is more stable. Again, you have to be reminded that I am dumbing these concepts down into high school level just so that you would appreciate. But again, the narrative plays out beautifully in the end. But the idea is you have weaker nuclear bond, less stable. You have stronger nuclear bond, you have more stability. Okay? And that's what I want you to see there. So therefore, if you look at this graph now, what you can say is that iron is the most stable element, specifically iron 56. And hydrogen is not that stable. It's actually weaker. It's less stable than, for example, helium, less stable than carbon, less stable than other elements that are bigger than that. And in fact, the most stable of all is iron. Okay? So, let's reroute back and say, talk about stability of things. Okay? In nature class, things always want to go from less stable states to more stable states. That's always a rule of nature. They will always go from less stable to more stable. So if you remember, let me just remind you some of the concepts that you've learned in chemistry in grade 9. For example, you have the nucleus here, and then you have the first energy level of electrons, the second energy level of electrons, the third energy level of electrons. You see, the third energy level is less stable. The most stable is the ground state, which is this one. So that's why when you have an electron and it gets excited here, it will always tend to de-excite and go to the ground state, because things always tend to go from less stable to more stable states. Okay? And again, there are a lot of reasons for that, more complicated concepts, but again, for high school level of understanding, this is enough to say that things tend to go from less stable to more stable. Okay? Another example that I can give you is if you have the ground, if you have an object on the ground versus an object hanging on away from the ground, what happens is this is more stable. Why? Because it cannot fall anymore. It's already on the ground. This is less stable because gravity is pulling it down. It can fall. Maybe something is holding it from falling. But the point is it's less stable because it can fall. So if it can fall, it is less stable, and that's why it has a tendency to fall down, because falling down means it will try to go into a state that is more stable. Okay? If you have a rubber band, you stretch it out. Stretching the rubber band is less stable. That's why it tends to retract back into its normal and stretched state, because that's the more stable state. So that's the idea here. So if you look at this, since iron is the most stable element, that means all the lower elements would actually want to become more stable to become iron. And if you look at the bigger elements like uranium, the energy of the bigger elements, the bigger elements are actually less stable than iron. So therefore, you have this pattern where iron is here, specifically iron 26, and then the smaller elements would want to would want to become iron to become more stable because it is the most stable element. And then the bigger elements would try to become iron so that they become more stable. Again, when I say smaller elements would try to become iron, I don't mean that they have intention, right? That they have sentient. What I mean by that is the process, it favors stability is achieved when smaller elements become bigger and achieve iron-like state. And the bigger elements would become more stable if they would become smaller and smaller and achieve the stability of iron. Okay. And again, this is not new in chemistry. Remember, you have if you have an element, let's just call it X, that element should have 8 valence electrons, right? That is what we call the octet rule. In fact, if you have an element like neon, neon has 8 valence electrons, and that's why neon is stable. And if you have sodium, sodium is element number 11. Meaning in the, sorry, let's repeat. Neon is element number 10. Remember, so element number 10 meaning in the inner it has 2 electrons because there are only 2 electrons in the innermost level, and then in the outermost level it has 8, and that's why it's stable. And then sodium is element number 11. So in the inner it has 2 electrons, and then in the outer it has 1, 2, 3, 4, 5, 6, 7, 8. That makes 10, but 11, it has 11 elements, protons, so it must have the 11th electron on the last layer. And again, what happens to sodium? Sodium wants to achieve stability. Neon is more stable. Noble gas configuration is more stable. That's why it doesn't like this extra electron. It gives it away. So if it gives it away, now you only have 10 electrons, but 11 protons. That's why sodium tends to become positive. For chlorine, it's the opposite. It has less electron. It has 7 valence electrons. So that's why it wants to absorb another electron. That's why chlorine tends to be negative, right? So you see, if an element has more electron, it wants to have less of it to achieve stability. And in the case of chlorine, it has less electrons than the ideal, which is 8 valence electrons. So it wants to get more electrons to become stable. So again, the same concept here. The same concept here. Because the size of iron 56 is the most stable, therefore elements that are smaller would want to become bigger, but elements that are bigger would want to become smaller, right? And so, how do you make smaller elements bigger? We just told you that. We fuse elements like hydrogen and hydrogen, hydrogen 1, fuse that, you make helium 2. 2 is bigger than hydrogen, so at least you have kind of drifted towards iron. Okay? And then, again, you get helium and helium, you fuse them, you get beryllium, beryllium and helium, 4 and 2, you fuse them, you get carbon. So you traverse towards this iron path, right? And that's why, if you look at the stars, hydrogen fused to become helium, the helium are fused to become carbon, the carbon plus another helium will form oxygen, right? And then oxygen will form silicon, and eventually it becomes iron. And guess what? When it becomes iron, will it continue fusing? It will not. Because remember, in the graph, iron is now the most stable one. So if you fuse iron and iron to make it bigger, it doesn't make sense because an element bigger than iron has less energy, so it's less stable. So I don't want to be less stable, I want stability. So let's stop at iron. So that's why all stars will always end up with an iron core. Okay? And again, more importantly, what is the process that makes smaller elements become bigger? You fuse things. So that's why fusion. And this is what happens in stars. You are fusing elements together and end up with iron. And on the other note, if you have bigger elements like uranium, uranium is so big. Uranium is, I think, let's see, 235 proton. Now, not protons, but 235 in terms of mass, or 235 nucleons. So it wants to become smaller. So how would you make a bigger element smaller? Well, if you have a bigger element, you simply divide it, right? So when you have a bigger element and it divides, it's kind of like a bacteria, one bacteria cell dividing into two. And what process do we call that? Fission. When a single bacteria kind of divides into two, it's fission. So when you have bigger elements trying to achieve stability, you undergo the process of fission. But if you have smaller elements, you undergo the process of fusion. And again, that's the reason why all fusion things would tend to have to end up with iron. And again, just in this manner, when you fuse small elements, you release energy. But when you have bigger elements, you put it under a fission process, you also produce energy. But it's different here by fusing, here by breaking up bigger elements, as long as it goes to iron. That's why in our technology for fusion, in stars we use hydrogen, helium, the smaller elements to make bigger to produce energy. But in our nuclear reactors that we use in Chernobyl, that we are using in the nuclear energy sector of the world, we are using uranium. We are using those bigger radioactive elements and breaking them up into smaller pieces to release the energy, right? So that's the idea. Now, why is this important? This is important, class, because if we know that stars undergo fusion, then we know stars can only produce iron. Okay, that's important. Stars can only produce iron. Let me repeat that. Stars can only produce iron. Meaning the energy in the stars, in the heat of the stars, in the pressure of the star, can only sustain and create iron. It can never create bigger elements than iron. But that's a problem because in Earth, when we dig up the crust, we find uranium. In fact, we are using uranium to make fission, right? So what gives? Why do we have uranium in Earth when, if we get the logic, the solar system, the Earth was coming from the formation of the solar system. Solar system was formed from a nebula. Nebula come from the super death of stars from previous generations, and stars in the previous generations could only create iron. So how come we have uranium? Okay, so that's the second half of the story. So here in the life cycle, remember, you create a supernova explosion in some cases, and this supernova explosion creates higher energy that it can fuse small iron. It can fuse iron into bigger elements. Okay, so let me get that straight because I know it's a little bit confusing. So it's like this. Hydrogen plus hydrogen, you get helium, and then you get energy. But in reality, this is not really what happens. What really happens is, to fuse hydrogen and hydrogen, you add energy, right? You add energy, and then once they fuse, they also release energy. So let's call this energy 1, let's call it energy 2. It's just that the amount of energy 2 is much bigger than the amount of energy you input, that it is sustainable, right? So again, let's review the concept of sustainability, the concept of getting more than what you have paid for. So to initiate the fusion, you still add energy, but when the fusion is done, it releases energy because it becomes more stable. By the way, if you're wondering, why would it release energy, sir? Would it be when it has more stability? Well, it's kind of like this. If you have this, right? This object is lifted on top of the ground, right? So it can fall. So it is less stable. It is more unstable. When it is on the ground, it is more stable because it cannot fall anymore. But in this configuration, it is less stable, right? But uh, look at what happens when I let this go. When I let this go, 1, 2, 3, go. When I let this go, what happens is this falls down, and when it falls down, it reaches the ground, it achieves more stability, right? So again, this is more stable, this is less stable. When it falls to the ground, it achieves its stability. But in the process, what happens? In the process, what happens? As this falls down, it hits the ground, it creates a sound. What does that sound represent? It means it released energy. Let me repeat again. When a less stable object achieves more stability, more often than not, it releases energy. In this case of something falling, it is manifested in the sound it creates, and in the as it hits the ground, it jostles the electrons here. I mean the particles here, so it creates some heat. So it releases energy. So the same thing. When you have a less stable configuration, achieving more stability, it releases energy. But make no mistake, to even initiate that process, you add energy. But it just so happens that for small elements, smaller than iron, the amount of energy you need to initiate it is less compared to the amount of energy you get out of it. That's why this process is feasible. That's why stars can keep on fusing until you get to iron. Because when you fuse iron together, even iron with helium, to create the next stuff, which is a bigger element, in this case, the amount of energy that you input is now bigger compared to the amount of energy that you get. That's why the process stops. So what we are trying to say is fusion of bigger elements possible, bigger than iron? It is possible, but it doesn't happen in stars, because in stars, if you try to do that, the amount of energy you input is more than the amount of energy you get. So therefore, it will not make the star burn longer. So that's why it's the end of the journey. But can you fuse the two? Can you fuse elements that would become bigger than iron? You can. The problem is you need more energy than you get. Okay? So, how do you get uranium? We have uranium on Earth, so it must have been created from somewhere. Yes, but it must have been created from a process that has more energy than in the star's core, because the star's core cannot provide that energy. And when does that happen? 1, 2, 3, go. Supernova. That's why it's called super, and it's not just nova, but it's called supernova because supernova explosions have very, very large energy output. Sometimes the energy output of a supernova is even bigger than the energy of the energy that's created by the lifetime of a star. Okay, sometimes, not all the time, but the point is, supernova explosions have more energy than what the core of a star can provide. Okay? So what happens really is, when the star is mature, like this, it's mature, it has a lot of iron already, this star will explode. And when it explodes, it will kind of push all of these things upwards. And the energy is so high that it's enough to fuse elements higher than iron. Okay, it is enough to fuse energies higher than iron. So maybe if you look at this core, maybe silicon and oxygen, or iron and silicon, when fused together, obviously they will make, sorry, when you have iron and silicon, when fused together, obviously they will make a bigger element. Again, it requires a lot of energy. That energy is provided by the supernova explosion. By the supernova explosion here. Without that supernova explosion, you would never get elements higher than iron. Okay? So what's the point? The point that we have uranium, polonium, other bigger elements on Earth that are naturally occurring. Barium. Meaning, the supernova, the nebula that formed the solar system was from a star that underwent a supernova explosion. Because if it was just an ordinary, not supernova explosion, then all the elements would be only up to iron. Because again, stars cannot create elements higher than iron. So that's why we believe the sun is a second or a third generation star, meaning there were earlier stars that have exploded and created bigger, heavier elements than iron, and that's why when those dust particles scattered, there were some barium, some uranium mixed into them, and then when they created the terrestrial planets, that's why we have uranium. Okay, so therefore, the solar system was created from nebula, which again came from supernova explosions from stars died in the past. So again, I like Neil deGrasse Tyson's way of saying it. He said that literally, as in literally, we came from stardust, right? Because if you think about it, it's the stars that died, scattered their remains onto the space, which became nebula. Then the nebula formed the solar system, and some of those were carbon, and those carbon created the human beings. So we are literally from stardust. But again, we know that elements up to the iron is created in the cores of stars, and elements higher than iron are created in supernova explosions. And the fact that we have elements higher than iron in the Earth, meaning the nebula that created the solar systems were older, and it has some mixed in elements that were created from past supernova explosions of past stars. Okay, so that's the idea. And again, there's still a loophole in this problem, in this thing, because the nebula that created the solar system came from an older star, and that older star eventually, if you trace it back, started with helium, with hydrogen, because hydrogen is the element that is in the core, that is abundant in stars. That is what is the starting point of all the fusion, right? That's a smaller element. But again, you have a question. So, okay, sir, I understand. Now we can explain where uranium came from, where all the iron, where all the carbon, where the silicon come from that we find on Earth. But ultimately, you have to trace it down to the starting, which is the hydrogen. So now the question is, where did the hydrogen come from in all of these stars? So that is now the next part of the video. But before I forget, I kind of actually forgotten it already, but I will show you this video about a supernova because um, what happens or what happens in stars is really this. It's kind of like everything else in science. Like, you know, if you have a string, you have a weight hanging on a string. Obviously, this object is being pulled down by gravity. But why is it not falling down? Well, because even if that object is being pulled down by gravity, by the force of the earth, it's also being pulled up by the string. So it's really a balance of forces that makes it like that. Right? If I'm holding this, it's not falling down because even if the eraser is being pulled down by a gravitational pull downwards, it's being pushed up by the normal force provided by my hand. So it's really a balance of forces. So why am I saying this? In a star, it's also the same. In a star, what happens is because the star creates fusion, it has force. The force of fusion kind of creates an upward push. Okay, and again, that's the reason why starlight will be radiated out. Okay, so you remember in fusion, it releases energy. It releases energy, the fusion process. So when hydrogen and hydrogen are fused, it releases energy, and that energy kind of gets emanated outwards, right? But the problem with that is if the star is emanated outwards, I mean, if the energy is emanated outwards, wouldn't the star expand and expand and expand and expand and expand? Because after all, the energy kind of would push it outwards, right? So here's the thing. Yes, it tends to does that to do that, but remember the star also has layers, right? And these layers are heavy. So the weight of the layers of the star would also try to shrink it down, right? So it's really a balance of forces. The fusion tries to the fusion energy tries to push it like that, but the weight also tries to push it like this, and it's a balance. As long as a star is alive, the pressure provided by the fusion and the pressure provided by the weight cancels out each other. Let's just look at one layer. So for example, this layer of the star, that layer is being pushed out by pressure provided by the fusion energy, but it's also being pushed down by its weight downwards the star. And for most part of the energy of the star, these two are balanced, right? The problem is when you have helium and helium, hydrogen, hydrogen, you form helium, and you notice this is heavier than that. So as this element, as this star matures, remember hydrogen becomes helium, becomes carbon, becomes oxygen, becomes silicon, becomes iron. And iron, remember, iron is heavy. So sometimes when the iron, when what is in the core is iron, it will not anymore produce fusion. So if it will not anymore produce fusion, the energy of fusion will become lesser, right? So if you look at this in terms of tug of war, weight, because remember that at first the layers are all helium, hydrogen, 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 hydrogen. But as hydrogen and hydrogen fuse, this becomes helium. So this becomes heavier, and this becomes carbon, this becomes oxygen. So the layers are becoming heavier, so the weight becomes bigger, but because the core has now become an iron, and this iron core becomes bigger and bigger and bigger, so iron cannot fuse anymore, so the fusion energy becomes lesser. So in terms of tug of war, the amount of energy provided by fusion will be overcome by the weight. Okay? So what happens? The weight wins. And if the weight wins, therefore the star collapses. Okay? The star collapses. And that is actually what a supernova is. It's a collapse of the star. Right? But then, sir, I'm confused. I thought supernovas are explosions. So now you're saying it's a collapse because the weight of the star is now greater than the outward push of the fusion energy. Then how come it explodes? Well, it actually explodes because of the collapse. So the collapse actually creates explosion. So think of it as um, when the layers collapse, when the layers collapse, the energy of the collapse causes the layers to bounce. So it's like they collapse and then they bounce, and then that bounce is a supernova explosion. So again, it's kind of counterintuitive. Why would a collapse of something become an explosion? Again, the collapse sorts of provides. Think of it as this layer and that layer are two balls. When you have two balls that hit each other, obviously they bounce. So the layers collapse, and then as they collapse, the force of the collapse kind of makes them bounce and scatter. And that's the explosion. That's the supernova explosion. And I will show you here a very good video about that. Now, this is from Physics Girl. Check her out. That's a very nice channel. So here she demonstrates that you have a ball. That ball is a basketball ball and how high it bounces. And then you have another ball, how high it bounces, and then a golf ball, how high it bounces. But if you stack them together, look at what happens. 1, 2, 3, go. 1, 2, 3, go. Look at how high the golf ball goes out. So that's actually is what happens to the layers of the star. So if you look at the layers of the star here, you have this iron, silicon. So the top of the star is kind of lighter, hydrogen, right? And then you come heavier and heavier. So it's like this is the basketball ball. This is the bouncy ball at the middle, and then this is the golf ball. So when it collapses, the collapse makes the layers bounce. And then the outer layer, which is kind of lighter, will be scattered all throughout the universe. And again, that's good because that means that if this is the star, the outer layers, which are lighter, will basically travel the farthest because they are lighter, and therefore they can spread the material. So if in this area of the universe there was no hydrogen, because of that supernova, now it will gain hydrogen because hydrogen is light and it can scatter far, far away, light years away from the original site of the supernova explosion. Right? So that's the idea. But again, returning to our dilemma, okay, because you explained supernova, our solar system, sir, came from a nebula. That nebula came from old stars that have exploded, and because we now understand how stars work, we now understand that the smaller elements, hydrogen up to iron, is created inside the stars, and then because of supernova explosions, the elements higher than iron up to uranium and those stuff are created in supernova explosions. That's why again in the Earth we have those bigger, heavier elements. But again, that begs the question, okay, you still, if we trace it back, so it still ends up with a star. It still ends up with a star starting with the material of hydrogen. So we have kind of expanded our knowledge beyond before the solar system, from the first generation of star, second generations of star, but we have not solved why hydrogen is there, because after all, it still starts with hydrogen. It still starts with a star. It still starts with a star with a lot of hydrogen, and hydrogen is the starting point. So how did we get hydrogen? That's what we will discuss in the next video.